Hi everybody, welcome back to the Feynman technique. So today I have an integral that both Wolfram Alpha and ChatGPT's O1 model failed to find the answer to. But we will be using complex numbers in combination with a result I derived in my last video. I will link to that video in the description. But the formula that I derived in my last video was this. Um, and this is fairly well known. I mean, you can look that up online. There's all sorts of different ways to show that. I used Feynman integration or differentiation under the integral sign to show that. And it might not be obvious how this applies to that integral right away. Obviously other than that x right there. But let's go ahead and continue, and you'll see why this is going to work out for us. All right, so let's choose the function f of x is equal to e to the negative x and apply it to this result right here. All right, so plugging that into our result, we see that this integral will evaluate to negative sine of 1 times the natural log of a over b. Go ahead and pause the video and work that out if you'd like, but that's what you get. Next, let's let our a equal I and our b equal negative I. Now, I have to admit that this step is a little unrigorous. There's probably, I'm sure there's more work that needs to be done to show that this is valid. Um, it it turns out it gives you the right answer, so maybe somebody could leave in the comments maybe a justification for why you're able to do this, but you are. I just tried it out and I got the answer that matches up perfectly with the answer that you get in Desmos. And Desmos just evaluates it numerically. And the answer that I end up getting with this method um, is that exactly. So, anyway, yeah, leave in the comments why this step is valid because I'm sure it is. But anyway, let's continue. So we're letting a equal I and b equal negative I. If you plug that in for a and b, you will end up getting this. All right, next step. We are going to express e to the negative ix and e to the ix in its trigonometric form. So we just write e to the negative ix as cosine x minus I sine x, and e to the ix as cosine x plus I sine x. All right, next we're going to break out the angle sum identities for sine. Um, and this is it. This is sine of a plus. We just use sine a minus b and sine a plus b, those two formulas, to get this. And then we subtract the results to get this. So we can replace this entire numerator with this. And we will do that. So now we have this integral right here. We have this equality right here. And now we just kind of need to figure out what sine of I sine x is. And we will use Euler's formula for that. Well, sine of ix, plugging that into the complex exponential representation of sine x, is going to give you this, which will in turn give you this. And this is simply the hyperbolic sine of x. So we can say that sine of I sine x is I sine hyperbolic of sine x. And we will just plug that in right there. And we are pretty much done. Plugging that in, we get negative 2 times this integral is equal to this quantity right here. And then we just divide both sides by negative 2i to get our final result of pi over 2 times the sine of 1. So there you go, guys. That is the answer. That is the value of that integral. Pi over 2 times the sine of 1. I hope you enjoyed that, and we'll see you next time.